Yeah, similarity, resistance, and also the matrix governing equation. So resistance is something I started 2 years ago and published in the paper last year. And matrix governing equation is something I'm currently working on, and I will talk about it in more details in Tuesday and Wednesday. Okay, so one of the key features for turbulence is that it contains countless many vortices of different sides. And just like what we can see from, this is a picture from the famous Da Vinci. And we can see like many vortices. Here is some big ones, and in the middle there are a lot of small vortices. And the whole process is described by Richardson in his poem, Big Words Have Little Words That Feed on Their Velocity, and little words has lesser words, and so on to viscosity. So the kinetic energy is obtained from the mean flow by these large vortices, and they are passing it down to smaller vortices through dissipation, and all the way into the molecule level where the kinetic energy will be converted to heat. And this process is also called the energy cascade. And Kolmogorov has 3 hypotheses about this process. So the first one, at sufficient high Reynolds number, which means it's fully developed turbulence, the small-scale turbulent motion with the length scale L is much less than L0 are statistically isotropic. So here L0 here is stands for the length scale of the largest eddies. And this L is just describing your current length scale, which means there is some pattern happens in these small scale motions that occur everywhere, and that is what we call similarity. And the second hypothesis is in every turbulent flow at sufficiently high Reynolds number, the statistics of the small scale motions, L is less than LEI, have a universal form that is uniquely determined by nu and epsilon. So here we said L is much less than L0, which means it will be convenient for us to set a boundary. So we call it LEI. LEI is like far away from L0 enough, and less than LEI, we say it's much less than L0. So actually, they are describing the same scale. And here, nu stands for the kinematic viscosity, and epsilon stands for the dissipation rate. And we can look at the third hypothesis. So in every turbulent flow at sufficiently high Reynolds number, the statistics of the motions of scale L in the range from eta much greater than eta and much less than L0 have a universal form that is uniquely determined by epsilon independent of the viscosity nu. So here eta is defined as nu cubic over epsilon to the 1/4 power. So the whole scale, we can separate it into 3 different zones. The first one is energy contained range. And it stands, it's from this capital L, which is the scale of the flow, to this LEI. And from LEI to LDI, we call it the inertial subrange. And beneath LDI, it is the dissipation range. And here EI and DI, EI stands for, E stands for energy contained range, and I is for inertia, and D is for dissipation, and I is again for inertial. So DI and EI, they are like boundaries for the inertial subrange. And for all the scales that is less than EI, we call it universal equilibrium range. And in the energy contained range, energy is, the kinetic energy is given by the main flow, and it goes to, and it goes to the large eddies. And in the inertial subrange, the energy is transferred from the large eddies to smaller ones. And in the dissipation range, this energy was dissipated into heat. And now I'm going to talk about the negative 5/3 law, which is also found by Kolmogorov. And let's just look at this diagram here. First, let's focus on the x-axis. First, this is a log-log plot, which means, so you can also see that from the x-axis, it's the exponentials. And the x-axis stands for the wave number, which is 1 over your length scale. So for large scales, it has less wave number around here, and in the middle, and then the small scales. So here we can see the energy is getting up in the large scales. That is in the energy contained range. And from here to here, this describing how energy is passing down from the large scale eddies to the smaller scale eddies. And after that, it's dissipated into heat in here. And this slope, it has the slope, this kind of straight line has the slope of negative 5/3. So this y value E of kappa can be written as C, some constant C, times epsilon to the 2/3 times kappa to the negative 5/3. And then when you take the log, it's some constant plus negative 5/3 log of kappa. And also we can find that for the straight line, the interception is decided by epsilon. So the larger the epsilon we have, the graph will look like higher. And this has been verified by many studies. And we can see they all have the same pattern, this straight line with slope negative 5/3. So now let's talk about the y value here. So that is the power spectrum density. And to understand what's up.
Be careful. This is for isotropic, not for boundary layer. Because that's general theory. This is for the.
Yeah, isotropic. Yeah.
This is for the isotropic, high reason number, isotropic.
Yeah, I think.
For boundary layer. I don't want to mislead you. This is be careful.
Okay.
This is not for the boundary layer, but most of the turbulence are for the boundary layer. So are called turbulence. It doesn't meet this law. This law for high Lewis number, large Lewis number, isotropic turbulence.
Yeah.
Be careful.
Okay. Okay, now let's talk about the y value, which is the power spectrum density. And to understand that, first we need to talk about starting from the discrete Fourier series. And after that, I will explain what's amplitude spectrum. And after that, we will look at what's power spectrum. And then we will talk about why we need this power spectrum density, this density idea. And then we will talk about Welch method, which gives us these spectrums. So first, this discrete Fourier series. So suppose we have a sequence. Actually, it should be starting from 0. So suppose we have x0, x1, x2, all the way to xn minus 1 as our signal. And then we can convert it from a time series or just a signal into a frequency domain value, which is capital X, x1, x2. So with this formula, so xk equals to the summation of j from 0 to n minus 1 of little xj times e to the negative 2 pi I kj over n. And here is an example. So this is code I read in Python. So here I said we have two major waves. One of them has frequency 17, and the other one has a frequency 47. And I set their amplitude to be 3 and 5. And totally we have 4,000 points, and the distance between each point is 1 over 800. And then we can, because this is Python, it has a built-in function to calculate everything. We just use FFT and then just plot it. So this is the signal looks like. And from here, this is the plot of the capital X0. And we can see we have a peak at here, which is around 13, and the other one at here, around 47. And the ratio of them is about 3 to 5. So another question here is, how can we retrieve this amplitude from the signal back from this capital X0? So here, suppose we have a wave which has a cosine 2 pi kn. K is some wave number or frequency plus b sine 2 pi kn. And then according to the formula I just gave, we times it with cosine 2 pi kn plus I sine 2 pi kn. And then we just multiply it out. So we have a cosine square plus ib sine square plus ia plus b over 2 sine of something. And when we summation it up, this sine, so if we simple enough number from a sine signal, eventually it will go to 0 because they will just cancel out each other. But for cosine square and sine square, they will not, since all the numbers are positive. So to get the average of cosine square and sine square, we can just
I was responding to a question.
Oh, okay. Thank you. So if we just integrate, actually the period for cosine square and sine square is pi, but it's okay if we use 2 pi. And the result will be pi. So which means if we sample enough points from cosine square and sine square, and we take average of that, the average is approaching to 1/2. So if we divide it by how many numbers we have, this capital N, xk over n will be approaching to a plus ib over 2. And then we can achieve this amplitude at this frequency on wave number k, which is square root of a squared plus b squared, which is also the absolute value of a plus ib. So it equals to 2 over capital N of the absolute value of xk. And here capital N is how many points do we have. And so this is the formula. And again here, it's same frequency, and then 2 times the absolute value of what we have, and then divide by total numbers we have. So here we can see the value became 3 and 5. And this is indeed the amplitude set in the beginning. And the idea of power spectrum is coming from the kinetic energy, which in physics, which is the mass over 2 times velocity squared. So here the power, we can treat it as the amplitude squared over 2. And then it will be 1/2, and the amplitude can be calculated from the previous page. And this is what we have, 2 times the absolute value square of xk and over n squared. And this is the plot of that. So it used to be 3 and 5. Now it should be 4.5 and 12.5. Now let's look at why do we need the idea of power spectrum density. So here is another wave I gave, and the amplitude is these integers, and the frequency ranges from, you can see it here, it's from 1.3 something to 1.6 something, all together in here. And we just apply the same method in previous page, and this is what we have. And we can find that we cannot achieve the information about the amplitude or the power from here anymore, because all these frequencies or wave numbers, they are so close to each other. So that's why we need the idea of density. How dense is this frequency or the wave number in this range? So the formula to calculate the power spectrum density is 2 times the absolute value of xk squared over f times n. Here f is your sampling frequency. So what I have here is like the distance between 2 points is 1 over 800. So f is 800. And it also equals to the power, which from the previous page, times L. L is the total length. And here it's just transform the unit from v squared into v squared over frequency or v squared over wave number. So it has the idea of density. And this is what we have if we use the power spectrum density. And in SciPy or MATLAB, we have a built-in function for that called periodogram. So we don't need to calculate everything in detail. We just use this built-in function and get everything. Now I want to talk about the Welch method. So previously, all these spectrums, we are treating the whole signal together as one window. The idea of window came from because if we're looking at the signal, we are not getting like all the information from negative infinite to positive infinite. We are only looking at it through a certain range. So it's like you are looking out through a window, and your vision is limited. And for Welch method, the first step is we separate it from the whole signal from one window into several segments, or you can call it sub-windows. So here I separate it into 5 windows. And this signal I just draw it by hand. It doesn't have any actual meanings. So here is just a diagram. I separate it into 5 windows, and we can see this one is actually the overlapping of these 2 windows, and this one comes from the overlapping of these 2 windows. And then for each window, we can times it with a window function to get a windowed signal. And after that, we just find the power spectrum density for each one of them, and then we average the result of all 5 signals. So what's a window function? So here we have several window functions. If you didn't apply any window function, then it's just the boxcar window. It's just a straight line. And here we have a triangular window, which is from 0, we pick to 1, and then go back to 0. And we also have Hamming window or flat top window. So we have 1 in the middle, and we have almost 0 at the boundaries. Suppose we have a sine signal here, and then we are using the Hamming window. And then we just multiply them together, get a windowed signal. So just multiply at each point. And we can find that in the middle, this signal is still ranging from -1 to +1, the same as the sine signal. But at these left and right ends, the signal gets attenuated, so it's approaching to almost 0. And that is the reason why we have this overlapping. If you have one signal that's some information here, it gets attenuated at the boundaries, and then in this one, it will be in the middle, which means it has the full percentage. And why do we apply this Welch method? So here is actual data of Lutex from our simulation. I use it as our signal. We have totally 1,920 points. And here we can, this is just a parallelogram, like I talked before, the building function. And here we also have building function for Welch method. It's just it's called Welch. And in MATLAB, I think it's called per Welch. We have a P in front. And X is just these numbers. And totally we have 1,920 of them. Here I told I want to use Hamming window. And for each sub-window, this one I set it, we want 640 points. And I want 50% of overlap, so that's 320. And scaling, I want to calculate the density. And here is the same, but for this sub-window, I wanted to have only 128 points. And then the overlapping is still 50%, that gives us 64. And then just plot the figure. So the blue one is we just use the parallelogram. And we can see it's shaking up and down, oscillating largely. And for here, we separate it into totally 5 segments. And we can see we still have some oscillation, but it's much smooth compared to the previous method. And if we choose an even smaller sub-window, we have more sub-windows. We have totally 29 of them. Now the green line is much smooth. And in our case, we want to find the spectrum for turbulence. And we want to find some common patterns from the data we have. So that's why we use the Welch method. And by separating it into several sub-windows, we actually sacrifice some information from the large scales. So, and by doing that, we can get some patterns that happens in common in the smaller scales. And that is what we call similarity. And now I want to talk about Lutex, resistance, and what is uniform decomposition. And for Lutex similarity, we will go back to it later. So suppose we have a scalar function with 4 independent variables, t, x, y, z. T stands for time, and x, y, z stands for the locations. And according to the formula for total derivative, it equals to dp equals to partial p over partial t times dt plus partial p over partial x times dx plus partial p over partial y dy plus partial p over partial z dz. And now let's just focusing on one specific particle. And by doing that, we are assuming that x, y, z is a function of t, which represents the location of this particle. And we can also find the velocity of this particle by taking derivative of x, y, z to t. So u is x prime t, v is y prime t, and w is z prime t. And UVW stands for the 3 components of the velocity in x, y, z direction. Then we can calculate the material derivative of p at this particle, dp over dt. So it's not just so we make it capital D because it's different from the total derivative. In here, total derivative x, y, z, t, they are independent variables. We cannot just divide by dt. But here, with this assumption, now we can divide by dt because x, y, z, they are just functions of t. So we divide by dt here. We have partial p over partial t plus partial p over partial x times dx over dt. Plus partial p over partial y times dy over dt, plus partial p over partial z, dz over dt. And dx over dt is actually just the velocity on x component, which is u. And here dy over dt is v, and dz over dt is w. So we get the formula for material derivative, which represents the change of p on this particle with respect to time. So here again, this is the formula we have from the previous page. And now let's study the accelerations for this particle, which is the change of velocity with respect to time. So the v over dt it's a vector. It's du over dt, dv over dt, and dw over dt. And for each of them, we just plug in the formula we have from here by replacing p to u, v, and w. So here it's partial u partial t plus partial u over x u plus partial u over partial y v plus partial u over partial z w. And then we can separate this first column, the first term, and we have u, v, w all in common. So we can factor that out as a vector. And that is what we got. So this term is partial v over partial t. And here we have a matrix. the velocity gradient matrix nebula V and times this V. So this is an acceleration of a particle, and according to Newton's second law, it equals to the F over m. So this term always appears on the left-hand side of Euler's equation or Navier-Stokes equation. So it's actually just the acceleration equals to force balance. So I know what Dr. Liu said about this velocity gradient matrix. In my opinion, I'm okay with both versions since there are many people using them. And just you need to state which one you are using and do not mess up the formulas, and that will be fine. So here we are going to study the eigenvector of this matrix. So we are using this version, partial U over partial X, partial U over partial Y, partial U over partial Z, this version. And next, so how do we get something from the original XYZ system into the principal system? We are using a special orthogonal transformation. So to convert it from the original system to the principal system, we just multiply U transpose and U on left and right. And after we transform this matrix into the principal system, we can decompose it into 3 parts easily at this principal system. And after that, we just transfer each term back with the same matrix here and back to the original system. And we have requirements for this matrix. It's called special orthogonal matrix, or called SO3 in algebra books. So U is composed by PQR, 3 orthogonal orthonormal vectors, and P is Px, Py, Pz, Q is Qx, Qy, Qz, and R is Rx, Ry, Rz. So for being orthogonal, U transpose equals to U inverse. And for being special, we want the determinant of U to be 1. So because for just regular orthogonal matrix, the determinant could be positive or negative 1, and here we want it to be positive 1. And that is something of Lutek's decomposition is different from the Schur's decomposition, because we have requirements for this orthogonal matrix. It's not just any orthogonal matrix. It has to be those ones with determinant of 1. And if it's a negative 1, it represents reflection. And for positive 1, it represents pure rotation. Now let's look at the discriminant of this matrix. So we can separate it into 3 different cases. When the discriminant is positive, we have 1 real and 2 complex conjugate eigenvalues. Or we can say for the characteristic polynomial, we have 1 real and 2 complex roots. And when the discriminant equals to 0, we have the repeated roots or repeated real eigenvalues. And in the first case, we just call it lambda r for the real eigenvalue. And lambda CR is the real part of the complex eigenvalue, and lambda CI is the imaginary part for the complex eigenvalue. So they are lambda CR plus or minus I lambda CI. And for the second case, we just call it lambda 1, lambda 2, or if we only have 1 eigenvalue, we just call it lambda. And in the third case, if the discriminant is less than 0, we have 3 distinct real eigenvalues, and let's just call them lambda 1, lambda 2, and lambda 3. And for the first case, it can also be classified into the rotational points. And for the second and the third case, we only have real eigenvalues. We can also classify them into the non-rotational points. So here is nabla capital V is the principal matrix, and it can be obtained. This is the original matrix in XYZ system, and this is the special orthogonal matrix for special orthogonal transformation. And after that, we got this. So we have lambda CR and lambda CR and lambda R on the diagonal. We have R over 2 plus epsilon. We have Kc here, and we have eta here. We have negative R over 2 here, and here is just a 0. And so if we have 0 for here, the requirement is this Rx, Ry, Rz needs to be the eigenvector for nabla V with respect to the real eigenvalue lambda R. And also we have requirements that omega dot R has to be positive. And the formula, I'm sure Dr. Liu has talked about it yesterday. It's equals to omega dot R minus square root of omega dot R squared minus 4 lambda Ci squared. Now let's see how do we get this formula. So first we can get this kind of vorticity matrix by using nabla V, the velocity gradient matrix, subtract its transpose. And then we can also find if we transfer this matrix into the original system, it should equals to into the principal system. It should equals to the principal matrix subtract its transpose. So the principal matrix subtract the transpose, it equals to, we have 0 on the diagonal, we have R plus epsilon, and negative epsilon minus R, and we have Kc here, negative Kc here, and we have eta and negative eta. So that should equals to the vorticity matrix, and we transfer it into the principal system. Now we just plug in these two matrices and multiply everything out. And here R plus epsilon is at the first column, the second row. So we multiply everything out from here and look at what we have at the first column, the second row. And this is what we got. And we can simplify it into omega x times the determinant of py, pz, qy, qz. And just simplify it. And here it equals, this equals to Rx, this equals to Ry, this equals to Rg. So that's why we have requirement for special orthogonal matrix, because only for those matrix we have P cross product with Q, that's R, Q cross product with R, that's P, and R cross product with P, that's Q. If not, you will have negative Rx, negative Ry, and negative Rg here, and that will give you negative omega dot R. And that is not what we want. So that's why we need a special orthogonal matrix. And similarly, we can get Kc equals to negative omega dot Q, and eta equals to omega dot P. Since PQR is also an orthonormal system, so we can write omega as omega dot P times P plus omega dot Q times Q plus omega dot R times R. And then we plug in eta, Kc, and epsilon. We have eta P minus Kc Q plus epsilon R times epsilon R plus R times R. And here the red part is the shear vector, and this r times little r is the Lutex vector. So that's why we have the vorticity equals to the summation of shear and Lutex. And since r plus epsilon is omega dot r, which means epsilon plus r over 2, that will be omega dot r minus r over 2, which is this number. And again, this orthogonal transformation preserves the determinant. These two matrices are similar to each other. So the determinant of nebula V is just the product of all its eigenvalues. So we have lambda r times lambda CR plus I lambda CI times lambda CR minus I lambda CI. And it equals to lambda r times lambda CR squared plus lambda CI squared. And on the right-hand side, we just calculate the determinant of this matrix. It equals to lambda r times the determinant of this little matrix, lambda CR squared minus negative r over 2 times r over 2 plus epsilon. And here we just cancel the lambda r, and we get lambda CR squared plus lambda CI squared equals to lambda CR squared plus r over 2 times omega dot r minus r over 2, because this number is here, we're just plugging it here. And then we can cancel lambda CR squared, and we got a quadratic equation for r over 2. And then we just use the quadratic formula to solve and to get the value for r. So r has like two solutions for now. It equals to omega dot r plus or minus the square root of omega dot r squared minus 4 lambda CI squared. And since there should not be any rotation, then the lambda CI equals to 0, which means we pick the negative sign here. Because if we have plus sign, then when lambda CI equals to 0, we still don't have 0 for the Lutex magnitude. So that's how we get the formula for the Lutex magnitude. Omega dot r minus square root of omega dot r squared minus 4 lambda CI squared. And now let's look at how the triple decomposition. So first we plug out the diagonals, lambda CR, lambda CI, and lambda r. This is for stretching and compression term. And then we have r over 2 and negative r over 2. This is for the rotation part. And we have epsilon, c, and eta. They stand for the shear. And for the first one, lambda CR, lambda CR, lambda r can be written as lambda CRI and plus another matrix with only one number, lambda r minus lambda CR at the lower right corner. So this equals to lambda CRI plus lambda CR minus lambda r minus lambda CR times r transpose. Here r transpose gives.
Can you go back one slide? Go back just one slide. When you have LCI equal to 0 and y this r, if you put lambda CI into that part, then you still get omega r, right? The last formula.
This one?
Yes.
If we put lambda CI equals to 0, and we assume that omega dot r is positive, omega dot r minus square root of omega dot r squared, which is it minus itself, that's 0.
Yeah, that's 0. So r is 0, right?
Yes, if lambda CI is 0, r is 0, yes. Because if lambda CI is 0, it's a non-rotational point. For non-rotational point, you don't have Lutex, right?
Yeah.
So yeah, that's true. Okay. And here, our transpose is actually a matrix, so formed by R and R transpose. And now let's look at the rotational term. Again, it's equals to this. So 1 over 2 Rz negative Rz, Ry negative Ry, Rx, and negative Rx. And actually, if you do the same process, you multiply everything out, it's about everything is related to P and Q, but we still have that formula, the cross product of P and Q that gives you R. That's how you get all these numbers. So actually, it's R over 2 times here little Rz, little Ry, and little Rx. And then you multiply it together, you have capital Rz, Ry, and Rx. And here Rx, Ry, Rz is the Lutec's vector. And for the shear part, it's easy. We just subtract what we have previously and just subtract them from the nebula V, the velocity gradient matrix. So this is the formula for it. Okay, now let's look at the second case. So for the second case, we have repeated eigenvalues. Let's just call it lambda 1, and lambda 2 for now. And we can achieve the principal matrix by starting from the first case and taking limit at let R goes to 0. So we have this term goes to 0. We have lambda CR, and R, and epsilon, Kc, and eta. And we can find these numbers on the diagonal is the eigenvalues, and we did have the repeated eigenvalue lambda CR. So for this case, we can say that we have conjugate complex numbers, but with 0 for the imaginary part. And then the decomposition is just we pull out the diagonal, lambda 1, lambda 2. So here lambda CR became lambda 1, and lambda R, we just rename it as lambda 2. We pull out the diagonal, and what's left is the shear, and this is stretching and compression. And if we only have one eigenvalues, which is a special case that everything equals to lambda. And again, we pull out the diagonals, and we have epsilon, Kc, and eta for the shear matrix. So to bring it back to the original system, we can use the same formula. And lambda CR became lambda 1, and lambda 2 is from lambda R. So it's actually the same formula. And here, R is the unit eigenvector of nebula V with respect to lambda 2. And for the shear matrix, we just subtract the stretching and compression from nebula V, since we don't have the rotation term. So we just subtract them, and this is the formula for it. And if we only have one eigenvalue, it's a special case when everything just equals to lambda. So the stretching or compression is just the lambda I, and the shear part is nebula V minus lambda I. Now let's look at the third case when we have three distinct real eigenvalues. So we know that fluids can have vorticity or shear, but not having rotation. So here we define a term called resistance, and we have a matrix for that, a symmetric matrix, and we just call it L. And the idea is once the non-rotational point is imposed by a rotational term, which is an anti-symmetric matrix, and the resistance will be consumed and be combined into shear, and to prevent this point from being rotated. So it's still in the third case. And once the resistance is depleted, it will be converted into case 2, and the resistance is also, so we defined it to be the minimum amount of rotation we need to transfer it from case 3 to case 2. So by using this idea, we will choose the eigenvector. On that direction, the resistance is the weakest as our principal axis R, because on that direction, the rotation is most likely to take place, and that is due to the bucket effect. So here is the principal matrix for this case. Again, we transfer it with this special orthogonal matrix, and this is what we have. On the diagonal, we have lambda 1 plus lambda 2 over 2. So, and the epsilon, c, and eta are the same. And here we have a symmetric part, L over 2 and L over 2. And here, this vector R needs to be the unit eigenvector of nebula V with respect to eigenvalue lambda 3, such that omega dot R is positive. And the formula to calculate that is square root omega dot R squared plus the square of lambda 1 minus lambda 2, and then subtract omega dot R. And let's see how do we get this formula. Again, we can use the principal matrix, subtract its transpose, and this is what we have. And different from the first case, now we don't have the R term. This L over 2 is symmetric, they will cancel each other. So we have epsilon, c, and eta, epsilon, negative c, and negative eta. And again, it should equals to the vorticity matrix and transfer it into the principal coordinate. And thus, by the same reason, we have epsilon, which is again first column, second row, is equals to omega dot R, and c equals to negative omega dot Q, and eta equals to omega dot P. So again, this is a orthonormal system, so omega equals to omega dot PP plus omega dot QQ plus omega dot RR. And we plug in the numbers, we have eta P minus CQ plus epsilon R, and that is the shear vector. So for non-rotational point, when your lutax is 0, vorticity equals to shear, because lutax is 0. And again, we have the similarity of two matrices, and then lambda 1, lambda 2, lambda 3, the product is the determinant of nebula V. It should equals to the determinant of the principal matrix, so that equals to lambda 3 times lambda 1 plus lambda 2 over 2 squared minus L times epsilon plus L over 2 times epsilon plus L over 2. And again, we can write it as the quadratic equation, and then we can solve it with two solutions. And we suppose there is no resistance when lambda 1 equals to lambda 2, which is the previous case. So we take the minus here. So when lambda 1 equals to lambda 2, we plug in here, we have lambda 1 minus lambda 2 is 0, we should get 0. So the formula will be omega dot R, so epsilon equals to omega dot R in non-rotational points. So omega dot R squared plus the square of lambda 1 minus lambda 2, and then take square root minus omega dot R. So that's how we get this formula. And to find the decomposition, that requires some more work compared to the first case, compared to the traditional lutax triple decomposition. So first, just like what I said before, we are looking for the minimum resistance for the matrix. And if by choosing different real eigenvalues, we actually have 3 different choices. So here, let's just call the 3 eigenvalues lambda A, lambda B, lambda C. And here we have the first one, let's just call it I. Li equals to square root of omega dot Vi plus lambda j minus lambda k. So Vi is the eigenvector for lambda I. And lambda j and lambda k are the other 2 eigenvalues. And we just plug that into the formula. We get the resistance at Vi. And then we compare all 3 of them. We see which one is the minimum. And we just call it L. So that one is our principal axis. So we just call lambda I as lambda 3, and that Vi became R, Rx, Ry, Rz, that Li became L. So how do we find the other 2 vectors P and Q? So this is an orthogonal system, and after we determined R, one of them, we get a plane. The whole plane is orthogonal to R. So now let's look at the plane. We can have the projection of V1 and V2 onto this plane, and let's just call it V1 prime and V2 prime. And in the principal matrix, we have lambda 1 plus lambda 2 over 2 on the diagonal. And if we want to achieve this, we need to pick the bisector of V1 prime and V2 prime. And V1 prime can be defined as V1 minus V1 dot RR, and V2 prime can be defined V2 minus V2 dot RR. And let's suppose n is a normalization of a vector. So we use a vector divided by its norm. Then we can find Q naught, which is a bisector. It equals to the normalization of V1 prime plus the normalization of V2 prime. We add them together. And then we can find P naught by using Q naught cross product with R. However, by using this bisector, we have several different choices. So if we have these 2 directions are the projected eigenvector, and then if we just pick the bisector, we have 4 choices. So these 2 red one will give you the same result, and these 2 blue one give you a different result. So if we pick a wrong system, we will have L over 2 at here and epsilon plus L over 2 at here. And we try to avoid that. So that's why, So after we pick up P naught and the Q naught, we need to verify that this is indeed the P and Q we want. So we use nebula V of Q naught dot P naught, which is the number over here. If it equals to L over 2, which means this we pick the correct vector, then this P is P naught, this Q is Q naught. Or otherwise, P is negative Q naught, Q is P naught. So after we pick the P and Q, we can convert it from the principal system back to the XYZ system. So for stretching and compression, again, this is the same formula. And on the diagonal, we have lambda 1 plus lambda 2 over 2. So here we have lambda 3 minus lambda 1 plus lambda 2 over 2. And here it became lambda 1 plus lambda 2 over 2i. And for the resistance term, So here, that's why we use P and Q, because if they are like L over 2 and negative L over 2, we can just get R, but here it's symmetric. We cannot get R again, so we need to find P and Q to get this term. And again, for shear, we just subtract the stretching or compression and the resistance from the original nebula V. And let's look at an example. If our velocity gradient matrix looks like this, and then we can find the vorticity is 1.5, negative 0.2, and negative 2.1. And I give a very special choice. The eigenvalues are just 1, 2, and 3. And we can find the eigenvectors is 1 over root 3, negative 7 over 5 root 3, negative 1 over 5 root 3. And this is for eigenvalue 1. And for eigenvalue 2, it's 5 over square root 35, negative 1 over square root 35, and negative 3 over square root 35. That's for 2. And for the last one, it's 0, 1 over square root 5, negative 2 over square root 5. And by using the formula we have, we can calculate the resistance at each direction. So at this direction, the first one, the resistance is 0.34 something. And the resistance at the second direction is 0.37 something, 73 something. And the resistance at the third direction is 0.26 something. So L3 is the minimum, which means this V3 is our principal axis, and this number is our resistance, and this 3 is our lambda 3. So, yeah, lambda 3 is 3, R is that, and L is this number. So we can find these two projected eigenvector by this orthogonal projection formula, and we get these two results. And then we just use the method I talked before, normalization of V1 prime, normalization of V2 prime. We add them together and do the normalization again. This is what we have for Q naught. And then Q naught cross product with R naught, we get this. That is, we call it P naught. And then we need to verify that whether this is the correct one we want. And luckily, nebula V of Q naught dot product with P naught is 0.13 something. That's exactly L over 2, which L, I remember, is 0.26 something. So that's what we want. So the stretching or compression matrix, we just plug in lambda 1, lambda 2 as 1 and 2 into the formula, and we can get this. And yeah, it's indeed a symmetric matrix. And for the resistance part, it equals to L over 2 QP transpose plus PQ transpose. And if we plug in the numbers, and this is what we have, and again, this is another symmetric matrix. And for the shear term, we just subtract the stretching compression and the resistance term from the original nebula V, and this is what we have. And if we cubic it, we got 0. That is because for the shear term, no matter it's for the first case or the third case, it's just epsilon, c, and eta. We have 0 on the diagonal, which means all the eigenvalues are 0. This matrix is nilpotent. For nilpotent matrix, you rise it to a certain power, you got 0 matrix. Now let's look at a little bit summary for this litex and resistance. So for stretching, so for the first case, when actually it should be positive. Okay, so the stretching and compression is just the diagonal for all 3 cases. And the property of this matrix is a symmetric matrix, and it has the same trace as the original matrix. And for the second part, rotation or resistance, the first one we have R over 2 and negative R over 2. And for the second case, when we have repeated eigenvalues, we just consider at 0 as 0. And for the third case, we have L over 2 and L over 2. This is a symmetric matrix. So the property of this matrix is it's either symmetric or antisymmetric. Both the trace and determinant of this matrix is 0. And we can notice this 0 matrix is both symmetric and antisymmetric. So that's why it's considered as the boundary case for both ends. And for the shear, it's just epsilon, c, and eta, and it's a nilpotent. You cubic it, you got 0. So now let's go back to the original assumption I gave. So for a non-rotational point, if we add a rotational term to it, but not very big, then it remains in the case 3, which means it's still non-rotational. So the fluids can take some shear, but without having rotation. So here we have this principal matrix for the third case, and we add A and a negative A, and we suppose this A is not too big, and that is what we have. And again, L over 2 minus A is still a positive number. And we can consider the new resistance as the original resistance subtract 2A, and the new shear at the V3 or R direction as epsilon plus 2A. So we can write it as this form, which is the same as the original, but with a new resistance and a new epsilon. So that's what I said. If we add a not too big rotation to a non-rotational point, we will increase the shear and consume the resistance. Now let's suppose we add a correct rotational term to it, which happens to be negative L over 2 and L over 2. And then we notice this became the second case. We have repeated eigenvalues, lambda 1 plus lambda 2 over 2, and lambda 3. So we just rename lambda 3 as lambda 2, and lambda 1 plus lambda 2 over 2 as lambda 1. We got the principal matrix for the second case. And if from here, if we add another rotational part, R over 2 and negative R over 2, and we can find that this became the Lutak's principal matrix for the first case. So, and again, we rename lambda 1 into lambda CR, and lambda 2 as our lambda R. Actually, resistance is more connected to Lutak's. So suppose we just consider lambda 1 and lambda 2 as lambda CR plus or minus I lambda CI, these two conjugate complex roots, and thus we have lambda 1 minus lambda 2 squared should be negative 4 lambda CI squared because there's an I here. And then negative resistance, we plug in the formula, it will be omega dot R minus square root omega dot R squared plus lambda 1 minus lambda 2 squared, and we plug in lambda 1 minus lambda 2 squared as negative 4 lambda CI squared. We got the formula for the Lutak's magnitude. And thus, we can get this conclusion, the negative resistance is actually kind of for Lutak's. And again, if we have lambda 1 happens to equals to lambda 2, then this gives you 0. Then we have 0 for the negative resistance. So that's for the second case. So together we can put this together for negative resistance 0 and Lutax together, Lutax magnitude together as one variable for both rotational points and non-rotational points. So this negative L can be used as a uniform parameter for both rotation and non-rotation points. And if it's for rotation points, we have Lutax. And for non-rotational points, this stands for the negative resistance. And now let's look at some papers about the Lutax similarity published by our research group. And this paper is called Lutax Represented Vertex Spectrum in Turbulence. And the data they use is cited from here. And it looks like some turbulence in a box. And then this is the spectrum. The first one is the spectrum for velocity magnitude. And we can find we have the slope -5/3 for most of them. And this one is for vorticity. And we can find that we have almost everything satisfy this trend, but this black line is top at here and then just go down quickly. So the black line is at y equals to 3, which means it's very close to the boundary. It's very near wall. And also here is for the, this one is for Lutax magnitude. And we have the slope here at -10/3. And because this is for the power, so for regular spectrum, we have -5/3. For the power, we square it, so we should have -10/3. And again, the black line is for y equals to 3, very close to the boundary. But here we can find it still have the same pattern as other lines. And also here it's for Q. So we can find this black line is not too small in the beginning and then decrease. Now let's look at another study from our group, which is this paper. And we are using simulation that looks like this. So this is a flat plate flow. We have a flow coming in the x direction as our stream direction. And y is for the span-wise direction. And z is for the height. And for this y, it's ranging from 0 to 22 with 128 grid points. And for the x direction, it's ranging from 300 something to 1200 something with totally 1920 grid points. And for z direction, I remember we have 241 grid points. And here they pick at several points and calculate the Lutax with respect to the time step. So this signal is actually a function related to time. And this 3 figure is the amplitude of Lutax, the spectrum for the amplitude of Lutax. So here he's using the amplitude, not power. We still have -5/3 slope. And this 3 is for Q. And we can find it has some pattern, but not strictly close to -5/3 slope compared to the Lutax case. And this one is for vorticity. And again, it has some pattern similar to -5/3, but not as close as the Lutex case. And we can find it more detail after we averaged it. So in his paper, he totally picked 15 points, and I just demonstrate 3 of them. And this is the average of many points, and we can find still -5/3 slope for the Lutex case. It's very clear. And for Q here, we can find quite big difference for Q case. And here this is case for vorticity. And again, the difference is pretty large. And I also did some research by myself, and I will talk about this later. Now I just want to talk a little bit about what I'm currently working on, the matrix governing equation. So here, this is in the tensor form of the incompressible flow of the Navier-Stokes equation, partial t of ui plus uk times partial k of ui. Here, k is double k stands for the summation. And it equals to -1/ρ partial I of p plus nu Laplace of ui. And then we can take another derivative, let's say partial j, on both sides. So we have partial j, partial t of ui, uk partial k ui, and then partial j of this term. So the first one, we can just put partial j into these brackets. So we have partial t of partial j ui. And for this uk partial k ui, we have to use the product rule. So we take the derivative of the first one times partial k ui. So that's here. So partial j uk partial k ui. And then we take the derivative for the second term. We have uk times partial k of partial j ui. And on the right-hand side, here we just put partial j into here. We have, we just call it partial ij of p pressure. And here is nu Laplace of partial j ui. And we can find partial j ui appears many times, and that is actually the velocity gradient matrix. So I is running from 1 to 3, j is running from 1 to 3. Partial j ui is the 3x3 matrix. That is the velocity gradient matrix. So here we just call it capital U for the velocity gradient matrix, partial j ui. And here p is 1/ρ. Here partial xx means taking double derivative on x for pressure. And we can just write it as pxx, pxy, pxc, and all the second order derivatives for p. So here this p is different from this pressure. This p is another variable, which is pressure over density. Because density is a constant, so we can just treat pressure over density as a new variable. And therefore, we get the matrix governing equation, d over dt of u, which is this term, these two terms, plus u squared. Oh, u squared is actually here. You can see partial j uk, partial k ui, and the k, we have two of them stand for summation. That's actually how we multiply the matrix, a row times a column. And here we have plus p minus nu Laplace of u equals to 0. Now let's look at some more details about the Lutex similarity I did. So here. And okay, so I'm using Python for coding, and this is for this is Jupyter Notebook. And let me see whether I can enlarge it. Oh, here. Okay. So here is just a subroutine to find the Lutex magnitude. And here you can, this is like the discriminant if less or equal to 0, which means we have 3 real eigenvalues. And here is actually to find the negative resistance, which I talked about previously. So here we have E1, E2, E3, which is the dot product of eigenvector with omega. And we are looking for the maximum of them because resistance, I defined it as the minimum. For negative resistance, we are looking for the maximum. And then here is just, we find lambda CR, lambda CI, and calculate the Lutec's magnitude. And here I just load data from our simulation. And we calculate this Lutec's magnitude is actually uniformed variable of Lutec's magnitude and also negative resistance together. Oh, okay. Okay, and then this is just use vouch to calculate that. And this is the result. So I picked 5 different depths, and at the grid point 20, 40, 60, 80, and 100. And this is the z value for them. And this one is very close to the wall, and this is just increasing. So this is the spectrum, and I'm using density, which means we should have the slope of negative 10 over 3. And here I just demonstrate 6 profiles, but actually we have 128 on the spanwise direction. So each signal is on the string x direction with 1,920 grid points. And this solid line is the average of 128 of them. And this straight line is just negative 10 over 3 to show the slope. And this is the 5 different depths, and this is the average of them. So we can find that this one is like the lowest. It has the minimum amount of turbulence or minimum amount of dissipation rate. And then we increase a little bit here. This is still pretty large. So we can actually find how turbulent it is by looking at how high is these spectrums. And I also plot the Lutec's and negative resistance, and we can find this one doesn't have many colors, so it's not that turbulent. And as we increase the depths, it became more turbulent and then decrease a little bit. So, and that's it. Any questions? Thank you.